So my talk will be a continuation of, in fact, Ming's talk this morning. And first of all, I would like to thank Karin and Jairo, who is not here, for this very kind invitation. And what I would like to do today is discuss these effects that Ming was talking about this morning, correlations and magnetism in unconventional superconductors. And I don't have a pointer. Oh, thank you. And I will also focus on iron pnictides. And in fact, I will go more to looking at the theoretical aspects. So how do we model these materials and their behavior? So how we get into these correlations and also the magnetism. And first of all, I would like to thank my collaborators and especially mention Stefan Backes, who was a PhD in Frankfurt and just moved to France, and Vladislav Borisov, who is a postdoc now in Frankfurt, and the experimental groups in Oxford, Amalia Kolde and Matthew Watson, with them we did a few R-pace analyses, and the group of Paul Canfield at Ames. So, in fact, we are interested in strongly correlated materials, and for us, strongly correlated materials are systems with strongly interacting electrons. That means that the electron wave function is very largely entangled. And one important property of correlated materials is, for instance, the presence of Mott insulators. In a Mott insulator, these are partially field band materials that, due to the strong correlation, they don't show a metallic behavior as one would expect in the case of having important screening, but they localize and show an insulating behavior. And one of the prominent examples of Mott insulators are the high TC superconductors. These materials are layered copper oxide materials, and as you know, they have a very complex phase diagrams. The parent compounds are Mott insulators and order antiferromagnetically, and when one dopes the systems, one observes the appearance of superconductivity with the highest TC, and many other phases that this morning already Ming was discussing. And here we know that correlation plays an important role. So in a one electron picture, we cannot explain this complex phase diagram, and the minimal model one can think of to discuss these different phases is the Hubbard model, where you take the importance of kinetic term, hopping term, and on-site Coulomb repulsion. Even though this model is extremely simple, there is, in fact, in 2 dimensions, no exact solution of the model, and for more than 30 years, people have been working on this model and variations of this model to understand the high TC cuprates. But today, I wouldn't like to talk about high TC cuprates. I would like to talk about iron-based superconductors that show a very similar phase diagram to the high TC cuprates. So basically, these materials are layered materials also, but instead of copper and oxygen playing the important role in the systems, it's iron and arsenic or selenium, so pnictide or the chalcogen atoms. And these systems are, in fact, metallic, but they show most of them long-range magnetic orders, so spin density wave-like. And by applying pressure or doping the materials, one can go into a superconducting state with TCs. The first one that was, in fact, observed in the group of Hosono was a TC of 26K. So just after the discovery of this superconductor, there were many other materials and classes. We had this morning a very nice phase diagram where all these systems were placed. As you see, the TCs have been going high. 55K was already a couple of months after the first discovery of these materials was seen in samarium 1111 material. And the highest TC reported up to now is an iron selenium monolayer on strontium tetranate. But this seems to be only one lab that has in this 100K, so there is no confirmation yet of this highest TC. And today I would like to concentrate on some of these materials to describe how we deal with the phenomenology of these systems. And I will present a very new class of materials that show an exotic magnetic state that was up to now not seen in the other members of the family. So initially, when these materials came out, the first analysis that one does is just like, let's look at the band structure and the one electron properties. And one sees already that these materials show Fermi surfaces which are small. Basically, they are characterized, so this is a cut along the K0 path. They are characterized by hole pockets around the gamma point and electron pockets around the M point. And one could see, in fact, that by many of these materials that show this spin density wave, that there are a lot of nesting properties by looking just at the Fermi surface. These systems are multi-orbitals in contrast to the cuprates, so all d orbitals of iron play a role at the Fermi surface and play a role in the electronic properties of the materials. And the superconducting order parameters, it's not the dx squared minus y squared like in the cuprates. Here, because of the symmetry of these systems, you have more options. And while most of the reports of superconductivity have been related to an S plus minus kind of order parameter, there are also reports of d-wave superconductivity. So we have more complex phase space for order parameters. So now what I would like to go back to also the 2 points that Ming was presenting. How important are correlations in these materials? So she showed us, in fact, how she can observe this correlations effect. And what I want to see also is to make the connection correlations effects to superconductivity and also the nature of magnetism. And since we are here in this Topology Matters in this workshop, I also tried to see where I put topology in my talk. So I will show you that, in fact, in these materials, there are now a new class of materials that have been discovered where one finds magnetism, which is a skyrmion-like magnetism. So maybe we can go here to topology. So and the kind of methods that we are using in order to describe theoretically these materials are a combination of density functional theory with many body methods. Now, correlations effects. Where do we see the effect of correlation in a metal? So let me just take now again this Hubbard model, this minimal model, and I'm just showing here the spectral function or the density of states at the Fermi level, as you like, and I'm going just to turn on in this one-band Hubbard model the interaction. So what does one see if I don't have interaction? So basically this is my bandwidth. Omega is proportional to the hopping, and I have basically a coherent quasi-particle peak. By turning on correlation, what happens is the effect of correlation is just making some transfer of a spectral weight from the coherent part to incoherent parts at higher energies, as we were seeing this morning, so that we are, in fact, renormalizing this quasi-particle peak and shifting weight into incoherent features at higher energies. And as we go to the highly correlated case, we will expect then this Mott insulator. So what we want to see is, in fact, whether we have these features in iron-based superconductors and how they, in fact, are contributing to explain the properties of superconductivity. Now, how do we deal with that theoretically? So in fact, there is the dynamical mean field theory that was proposed a long way back by Antoine George, Gaby Kotlia, Dieter Volhard, and many other contributors to the field, where the idea is to just include correlations in a non-perturbative way by substituting your interacting lattice in terms of one atom in this lattice dynamically interacting with a bath. And what is important is this dynamic interaction, because this is then giving you an exact description of the local correlations in these materials. So with this method, you have a good description of the local effect of correlations. And now the idea is to just make assembling together this inclusion of correlations with density functional theory, which gives you a basis of the chemistry that is there being important in your material. One issue that we just saw with these iron pnictides is that these are multi-orbital systems. That means that this kind of one orbital description is not enough. So we need to include one more energy scale into the description, which is the Hund's coupling. And the Hund's coupling is going to play an important role in these materials. And the first person to, in fact, bring this concept of Hund's metal for the iron pnictides was Gaby Kotlia and his collaborators. And I'm not going to go very deep into the Hund's metal features of these materials, but I'm going to just show how these features come in when we try to describe the systems. So we saw this morning that the traces, where do we see in experiment these effects of renormalization of bands and incoherent parts at higher energies, so for instance in Ironbased. So here I'm showing this extreme hold-up case of 1 to 2 materials. So basically this is the structure of the material, and I'm having here potassium instead of calcium. Since it's an extreme hold-up, it means that in this picture that I was showing you for the Fermi surfaces, I'm losing the electronic pockets at M, and the system only has hole pockets. Now these are the measurements, the Ironbased measurements at k equals 0 and at k equal pi. And this is just basically a DFT calculation with LDA. And one observes that there is the LDA is not enough to explain, in fact, the topology of this Fermi surface. So if you now really calculate with dynamical mean field theory so that you include the effects of the interactions in terms of self-energies, you recover what is seen experimentally. You recover, in fact, these here flower-type features. And of course, this looks blurred. It's blurred because now we have the effect of the self-energy. So therefore, we don't have anymore these peaks that you would have, these delta peaks that you would have in LDA. And what is important here is that what we do have is orbital selective correlation. So the different orbitals are renormalizing differently, and this can be understood by the fact that in these structures, whether there is the interaction in the plane or out of the plane, I'm going to have different kind of hybridizations that are going to correlate more or less the electrons belonging to the different orbitals. And this we can measure in terms, for instance, of the effective masses, that one sees that the dxy, the in-plane orbital, is the most renormalized band, while, for instance, the dx squared minus y squared is the less renormalized one, which is the one that goes just 45 degrees to the dxy. So these orbital selective correlations, one can also observe that by analyzing whether this material shows bad metal behavior. So we know that if we have correlations, the picture of having well-defined quasi-particles breaks due to this self-energy. So, and here what I'm showing is the calculations at different temperatures of the inverse of the quasi-particle lifetime. So if we are at very high temperatures, different orbitals have different quasi-particle lifetimes, and we see that the inverse are very large. So that means that, so this is the scattering rate. So that means that at very high temperatures, I do have, in fact, a very incoherent state. So I will have a bad metal, and going down in temperature, when I get that the quasi-particle lifetime rises, so this definition or this description in terms of quasi-particle wins again, and I go into the Fermi liquid region. And what I wanted to show here is that, in fact, this is very much orbital dependent. And experimentally, it has been measured, this coherence-incoherence crossover, for instance, in resistivity and specific heat. So I'm showing here the resistivity in this from 0 to 300 Kelvin. So usually for Fermi liquid behavior, you expect that the resistivity goes like temperature squared. And you see here that about 70 Kelvin, it just deviates from this T squared. So that you could interpret that as a deviation from Fermi liquid, so that you start having a bad metal. At low temperatures, you regain, in fact, this T squared behavior, the Fermi liquid behavior, and then, of course, the system superconducts at very low temperatures. So basically, we have here the feature of bad metals that one observes also experimentally. One can explain it in terms of these orbital selective correlations. Of course, there is a second feature right now. So we were focusing very much what happens in the renormalization of basically the bands at the Fermi surface. But there is this transfer of a spectral weight as the correlations get more and more important to these high and low energy, so away from the Fermi surface. And the question is whether this is possible to be observed experimentally. So in fact, the question is whether RPAs can observe this incoherence weight away from the quasi-particle peak. And this is, in fact, the experiments that Matthew Watson, Malia Koldea, and their collaborators did in Oxford. They took, in fact, iron selenium, and they measured how is the evolution of the spectral weight as so going down, so they're going to higher binding energies. And they find, in fact, the presence of so this is the quasi-particle peak, then there is a dip where there is no weight, and then the appearance of the lower Hubbard band, which agrees with these LDA plus DMFT calculations. So the DFT calculations are basically these black lines where, of course, you don't have the effects of correlation. Now you include them at DMFT, and you get these features of the lower Hubbard band. And this has been also confirmed, these experiments by Borisenko and collaborators. So in fact, these materials, you can see these effects of incoherent tails at higher binding energies. And what is, of course, interesting here, again, is that the contribution to these incoherent weights is different for different orbitals. So one can analyze that in terms of the calculations, but also by doing different polarized RPAS experiments where we could follow basically this transfer of spectral weight for the different orbitals. So this was, again, a confirmation of this different renormalization of bands. And I would like to mention that very recently, in the group of Seamus-Davis, they have been able, by using quasi-particle interference imaging, they have been able to see that the Cooper pairing that happens in the superconducting state is in fact orbital selective. So again, we have that the features of this selective orbital selective correlation goes into the superconducting state. So this was the part of correlations that I wanted to just show how, from the theoretical point of view, we can try to understand or try to describe the experimental observations. And of course, an important part, so I was mostly here in this tetragonal phase, but an important part of these phase diagrams of these materials is this magnetic phase. And in fact, this is, as Ming was also discussing, analogous to the cuprates. Even though the cuprates here, we have an insulator, we do have magnetism. And the question is, which is the influence of magnetism, so not only correlations, but also magnetism on the superconducting state? So what I want to discuss a little bit is the nature of magnetism in these materials. And I'm going to do that by looking first at the options that we have of breaking the symmetry in these materials in different ways to try to find the corresponding long-range magnetic orders for these materials. So all these materials, so these are the various families that we have seen of iron-based superconductors. They all, at the high temperature phase, they are all tetragonal. A equal to B, and they are either primitive center or body centered. And what I want now to concentrate is on two special symmetries of these space groups. And the special symmetries are the C4 symmetry, so that I have this 90 degrees rotational symmetry in this tetragonal symmetry, and also the fact that I have a glide symmetry across the iron arsenic plane. So you see here, if you just do a translation of half a unit cell, and then you just do an inversion, you recover the same symmetry. So this is our glide symmetry. And what I'm going to do is analyze breaking of these symmetries, what kind of long-range magnetic orders we could get out of that. So let's start here. What I'm showing is from the top, I'm showing this plane of iron with selenium or arsenic. Selenium on the top is in green, selenium on the bottom is in this, call it violet. And I'm showing here, in fact, how are the possible orderings if I break this rotational symmetry. So if I go to a C2, so I go to an orthorhombic, so I do a little structural structural distortion and also break time reversal symmetry, the kind of order that one can obtain is a stripe order. So in a very general way, for all these materials, magnetism can be, in fact, written as a linear combination of two different wave vectors, pi 0 and 0 pi. So in this stripe order, when I break the C4 symmetry, basically one of the two is 0, and what I have automatically is a stripe order. So that means here it's antiferromagnetic along the A direction and ferromagnetic along the B direction. So it would be the case of the pi 0. And what I'm showing here in this, for the selenium and arsenic, this going in or out, is just the hyperfine fields in selenium and arsenic, in case that, for instance, we want to distinguish between having the ordering of the iron moments parallel to the order parameter of the perpendicular. One can measure that by doing NMR, because one can see the contribution of the hyperfine fields of selenium or arsenic is going to be different for these two cases. Now, the second order that was this morning very nicely introduced by Ming is this spin charge density wave order. So where Ming finds also charge ordering, where the C4 symmetry is preserved, and one can obtain that by doing this linear combination of M1 plus M2. So that we have then that the magnetic moments go perpendicular to the plane, and they are doubled. And this is compensated, so it's 0 and doubled 0. That's why it's called spin charge density wave or double Q order. And there are examples for this order and for this order. Most of the materials show this order. But there is now a third order that one can think of theoretically, is if I break light symmetry, so basically I'm breaking inversion symmetry, I have a third option. And a third option is, in fact, starting to having non-collinear type of orders, like a Hedgehog order or a spin vortex crystal. So this would be 2 in, 2 out, and this would be just in, out, in, out. So basically showing a kind of loop. So these are theoretically possible states. If I break this symmetry, these are allowed states. Up to now, there was no observation of this order, but I'm going to show that a few months ago, this was in fact observed in a material. So let me spend some slides, I have some time, first on the stripe order. The stripe order is especially interesting because associated to it, we have this pneumatic order. So the stripe order, if we look again at this order, so I'm showing now only the iron plane, and here I'm showing the stripe order with this propagating vector 0 pi, so ferromagnetic along the A direction and antiferromagnetic along the B direction. And we see that in order to get this order, we have to break this rotational symmetry, and of course, because it's a long-range order, time reversal symmetry. But we can observe that this order can be seen as two Snell orders being interpenetrated. So just look at the yellow and the green arrows. So the yellow arrows form a Snell state, and the green arrows form a Snell state. So I have these two interpenetrating Snell orders, and this already tells me that excitations to this state will be when I start to basically have some fluctuations of these two orders. And this is in fact what is the pneumatic order, and was initially observed by in these dope 1 to 2 materials, that there was this region near the stripe face where we do have an order where we break this C4 symmetry, but we don't break long-range order. And this comes from the fact that these two lattices are starting to fluctuate. So this is a very important order. So we preserve time reversal symmetry. There is no long range, but we are breaking this symmetry. And there has been a lot of discussion about the origin of these pneumatic orders. So what produces these excitations? We have various degrees of freedom, of course, the structural distortion, but Ming was showing this morning that the structural distortion is tiny, and we get very strong response, for instance, in anisotropic resistivity. It's charge on orbitals or it's a spin. And there has been different groups promoting one or the other. So in fact, these are all very entangled degrees of freedom. So all of them are playing a role. But definitely, it's an electronic nematic order. It's not the structural distortions. It's basically the interplay of spin, orbital, and charge. And there is one very extreme case of nematic system, or system showing nematicity, which is iron-selenium. In iron-selenium, the phase diagram, and I'm showing here the phase diagram as a function of pressure, has a very large region of nematicity. It doesn't show stripe order. It's nematic, so the system goes from a tetragonal to an orthorhombic phase, but then it gets nematic. There is no long-range order. And then superconductivity shows up at about 8 Kelvin, and as a function of pressure, the superconductivity goes up. And this, in fact, at the beginning, there was a lot of unclearness how to understand this phase diagram, especially because if we look at all of the materials at order, superconductivity, the TC always goes down with pressure. So how this happens here? And where is the origin of the nematicity? While there is no stripe order or long-range order appearing in the system. And there are many, I'm not going to go into detail to this, there have been many different experiments analyzing this nematic phase. And let me just show you what can we learn from ab initio calculations shortly about this nematic state. So of course, a DFT calculation doesn't include the fluctuations that we need for nematicity. But what we can understand, or what we can analyze, is different magnetic states and see, in fact, which are the energies of these magnetic states. So whether there is some degeneracy of magnetic states. So what we found for iron-selenium is this is our stripe phase. So basically, you have this down and up spin, so ferro and antiferro. So what one finds is, and this would be the pi zero state, that if you analyze the ground state energies of states where you just start to make this second, so the y term of your q vector incommensurate, so pi half, pi third, and you go through all the series, all these states are in fact very degenerate. So here I'm showing the energies. So this is telling us that we have, in fact, all these states are competing. If we want to interpret the fact that we have degeneracy in energy, all these states are competing, but they have a very special propagating vector. So that we would understand that this nematicity is very much related to having a magnetic frustration in this material. And we could understand from that, in fact, this magnetic frustration preserves nematic order because you break the C2 symmetry, but because of the frustration of which should be the Q that gives you the ground state, the system remains nematic. There is no way for the system to decide which is the state that is going to stabilize it. But if you now apply a pressure on the system, what you find is that the system, basically the energy that wins is the stripe order again. And this agrees with the phase diagram. So what we see is in this region of nematicity where we have these basically strongly degenerate states, you wouldn't expect any long-range order, and superconductivity should appear at very low temperatures because they are pair-breaking, these spin fluctuations. But as soon as you apply pressure, the fluctuation, so the Q vector that wins is the pi zero, and this is the one that promotes S plus minus superconductivity, and that's why one could try and understand this rise of TC. So just telling you that there is, in fact, in this material, it's very special because of this appearance of magnetic frustration. And the question is, why is this system so special? So if we look, we looked here also at this one parameter that Ming was also describing this morning. Let's look at basically at the distance between the iron and the arsenic and selenium. In these materials, electronic properties are extremely dependent on this distance. So it changes the magnetism of these materials very strongly. And we see that if the distance is below, let's say, 1.45, they all order in stripe order. But the precise position of selenium and iron is very critical. So it's at this critical distance where you observe this magnetic degeneracy. If you just push it up again, you get two other orders that have also been observed experimentally. So of course the system is more complex than that, but I just wanted to put it into one parameter where you can see why this degeneracy comes in, and then of course pneumaticity and what it comes with it. And in my last two transparency, let me now go to this new state that theoretical, as I was showing to you, if I just break this glide symmetry and time reversal symmetry, I should be able to realize a planar hedgehog. So I have to be careful because this is this planar hedgehog type of order. And this, in fact, has been discussed a lot at the level of just group theory. And recently, the group of Paul Camphil, basically they synthesized this material. So the idea, this is just a 1-to-2 material. So you take again these iron arsenic planes, and now instead of having calcium all over, you just break explicitly this inversion symmetry by alternating calcium with potassium, calcium with potassium. So now you have broken the symmetry, and indeed, when you start doping the system, what they find is that they stabilize the phase where the order is this Hedgehog order. So this non-collinearity then appears, and one can in fact observe that this is the order. For instance, in NMR, they have been determining, in fact, the corresponding hyperfine fields. So you can observe that this is the order that one obtains. And if we have done the calculations of that, in fact, this is the order that stabilizes for the conditions of this material. So we have now also in the iron-based superconductors this kind of non-collinear orders that resemble skyrmion type of orders. And the question is, which are the consequences then for superconductivity? I mean, this is ongoing work. And since my time is over, I go now to my conclusions. So I also chose these two aspects of iron pnictides, what are correlation effects doing on iron pnictides, how they are influencing the superconducting properties. And what we saw is that by using, for instance, the combination of ab initio with many-body methods, one can explain this strong band renormalization seen in Ironbased, and one finds these very strongly orbital selective correlations. And of course, this changes the Fermi surface topology. So this influences, in fact, the description of superconductivity. And there is this recent work of Siemens-Davis where they can observe this orbital selective Cooper pairing. And moreover, that one can observe, in fact, these incoherent features that nobody talks about, but they are there and have been observed in Ironbased. And magnetization in magnetism, so by starting with the most general way of describing magnetic order in the iron pnictides in terms of two Q vectors, pi 0 and 0 pi. In principle, we have three possible magnetic orders. Most of the materials, when they order, they show stripe order. And with stripe order, we have this associated pneumaticity because of these interpenetrating nil lattices, sublattices. We have this double Q order that has been seen now in many whole dope 1-to-2s. And this is now the new system coming into play, which where we have Hedgehog or skyrmion type of order. I would be very careful in saying this word skyrmion in this community, but basically that we have this 2-in-2-out non-collinear order. And we have to analyze which are the consequences for superconductivity. And I thank you for your attention. I'm fine with the time.